Yakunin. I'm the CTO of Service Titan, and I'm going to talk about a technology that allows you to build real-time apps and web apps, Blazor apps, uh, without actually, I mean, with nearly zero cost of real time. So, let's start. Uh, I, I just a moment. I guess I have to share the screen. So I'm not sharing the, should I share the sound? Okay. Uh, mm, mm, mm. Can you see the screen?
Yep, looks good.
Okay. So, but first, I guess, let's think a little bit of, um, or like talk a little bit of the cost of real time. And I usually present Twitter as an example of something that implements real-time features. So here is an example. I click on like button here, then I declick this one, and everything is fine for now. And now this one, and you see that it shows that the tweet is deleted and like count is displayed. I mean, the like counter displayed is correct, but it's actually not always the case. And if we are going to look at kind of worst possible scenario I saw, I mean, it wasn't editing of like HTML or something. You may see -1 likes by doing merely this. So now I'm going to show a brief demo of an app built on basically the technology I'm going to talk about. And sorry. And just to kind of show how it works here. So it's board games. I'm running it locally, and I click start a new game here. These are two different user accounts. So I want to highlight this somehow to another user, right? And first I make it public. You see, like, it's public here. Oh, okay, I actually clicked on row. So it's public here, right? And so I typed an introduction message, and you see it's there, right? Uh, and I type a message here, and you see it's displayed, right? And then I can click here, join the game, and it starts. So I'm making some moves, and basically, yeah, that's nearly how it works. And even if I do something like this, and when I go to profile of this user and change his name, you see, right? The other person sees the change. So okay, now let's get back to the presentation and talk about how all of this stuff works. Yeah, that's a summary of what I'm going to talk about. I think there are a few different or like seemingly different topics that I'm also going to cover because all of this is related to caching and invalidation and eventual consistency. But overall, it's more about real-time things. Okay, so now let's think how we kind of build a typical UI, right? Usually our UI fetches the data from client, which fetches basically similar data through the API from server-side services or microservices, and basically they fetch them from different storages. And interestingly, the state with updates is kind of way more complex, because if you want real time, right, then you need to somehow describe all the events that happen in your app or basically have something like domain events, and you need to teach your UI to um, process these events in such a way that they change everything properly, right? And this is complex. It's actually like yeah, crazy complex, because basically the larger is the app, the more of such events you get, and moreover, the interdependencies between basically parts of the UI and the events are like also getting more and more complex. So in other words, it seems like if you want to just display the stuff, it's easy. And that's why we mostly build apps that just display the stuff. But if we want to make everything real time, then it's getting complex. And by the way, if we look just about reads, then everything looks like a sort of production plant or supply chain, where basically in the end, there is a UI, a customer, right? And basically the data goes through several stages of processing and transformations, and eventually like you see the HTML or something, right? But the stream of data is very, very kind of direct. It's basically either directed a cyclic graph, right, or maybe even a tree. So the question is like, why we don't build UIs like this? Why we don't write, or like why we can't just write functions that are more or less pure functions, right? That basically get wherever they need and pass it to another stage. So like in this example, let's say we could have a function that renders the whole UI. It returns a string. It's an HTML of the page. And this function, for example, may call render user name, right, which also returns a string, but hits the endpoint to get the data, right? Then like this endpoint, I mean, that we hit get user, it may, it basically may, just a moment. Yeah, okay. I checked out what was the question, sorry. So, and this endpoint may get the user data from some repository, and so on. So why we don't build basically apps like this? And the answer is actually very simple. Well, it's quite expensive to recompute everything on every attempt to display whatever we build, right? And moreover, it's time consuming because, for example, here, right, this is an RPC call, and it just like unfeasible to run lots of such calls per every render. So we kind of do it differently. On the other hand, if you kind of think of all these problems, then you will quickly discover that nothing is new there, in sense that expensive to recompute means we need caching, right? And time consuming, again, it's also kind of like if we have client-side caching, then maybe we just don't need to make all these calls. So, and that's just a fancy slide that we actually cache kind of more stuff than we think. Okay. So now let's talk about how we could solve this. And this section is going to be probably the most kind of intense in terms of like your brain activity. So I'm going to show a very simplified example of what Fusion actually does. And Fusion is the library I'm talking about. And it's super kind of simplified in comparison to what it actually does, but it kind of illustrates the main idea. So let's say we want to write something that transforms all our functions into functions with caching. On top of that, I mean, functions that don't recompute the same result twice, basically. And there is a concept of decorators in some languages. Basically, it's a function that takes another function and transforms it into a function with identical signature, but adds some behavior on top of that. So this is an example of such decorator, right? It basically takes this function, right, and transforms it into this function, which Well, does a few things. So basically, it creates a key that I will use to kind of check what's in, and you see, by the way, that this key depends on basically the reference to this function and its input. So somehow it kind of encodes all of this. And then it looks into our cache using double check locking. And if it finds nothing, then it computes the value and puts it into your cache, right? And if it finds something, then it returns here or here. So basically, that's a simple caching decorator. You probably used something like this a few times, or maybe you saw it somewhere in some libraries. And now the question is like, so what's wrong about this caching decorator, and like, or what's the downside of this? And the downside is that, well, it only works when the function we pass there is a pure and moreover deterministic function. And we don't have many of such functions actually. So how do we solve this problem? And like plan A is quite functional, I mean, in terms of style, right? But it's hard to actually implement. And there is also a plan B that allows us to basically fix this decorator and add some extra to make it work with non-pure and non-deterministic functions. So let's see how we can do that. Okay, so this is another decorator. As you see, it works in a similar style. And by the way, like right from basically few next slides are going to be kind of tricky. So on a high level, it does almost the same thing as the previous one. Basically, again, it checks if the value is in cache. And I mean, you might see from the signature here that what it gets from cache is not exactly the value itself. It's basically a box that stores the value, but this box also does some extra. So, but if it doesn't find something inside the cache, right, then it does. So first, let's look kind of into the inside of try. Basically, it computes the value, right? But before computing it, it actually publishes the box that it's going to use to store the value using something like, let's say, thread static or thread local. And basically, it makes it available for code that will run here. And once it completes the computation, basically it stores the value and returns what's inside the box using a special construction. So now the question is like, what basically, what is this and what is this? I mean, what are these functions? Okay, so let's start from a simple one. So use means we want to declare that, like, basically the value we fetch here should be consumed by a parent, basically, or like should be registered as a dependency of a parent computed value. So like if we compute something, right, and for something else we call use, then what we compute will know that there is a dependency. Okay, and I'll get back to use, or actually let's basically look at this. And interestingly, the second version of use, use or invalidate, has a special block. So basically, this block means that if right now we, let's say, are inside invalidation context, then we need to do completely different thing. We basically, instead of returning the current value, we will invalidate it and return basically anything we want because it's not going to be used. But if we outside of the invalidation context, then we are going to just basically use the value. So now why it's going to work like this? First, like you saw, that invalidate call is here, right? So what invalidate means? Well, invalidate means that we, first, again, we kind of check the state, and if we invalidated the current value, then I guess we don't need to do anything. But ultimately, what we want to do here is to run a cascading invalidation. And this means that we will invalidate the current value, remove it from cache, and trigger basically the same thing for all the dependencies of the current value. So if you saw like this construction, then this means that basically these links are actually bidirectional. So not only the value knows what it depends on, but also it knows what depends on it. So, and this thing kind of runs the invalidation on dependence. Okay. And now finally, what is invalidation context? So you see that this is a static function. Basically, it's not the same as this thing, right? And we basically, what we do here is that we, so computed is invalidating is actually also a sort of thread static, right? And we just declare that inside this block, it's going to be true. And we will call an action that we want to perform inside this block. And wherever this action tries to fetch or invoke using these tricky methods, right, it's going to be invalidated. I mean, basically, you see that like once it gets to this if, it will end up here if this block is on, and in turn it will end up here. So basically, instead of retrieving the value from cache, if it exists, it will invalidate it, right? And if it doesn't, then it just like will return nothing. Okay, so let's move on. So now, how we can use this stuff? We can do something like this. So let's say we have a function that fetches a value from a dictionary, right? And like you see, there is nothing tricky here. It just directly fetches the value from a dictionary. We'll call this function getCounter, but like the only extra thing we will do is we will apply this decorator to this function. Then we will declare the second function. Basically, it will call the first one, right? But there is a typo. So there should, this getCounter should be small. But anyway, so we basically call the first function here, right? And also decorated by the same decorator. And finally, like if we call it twice, basically what's supposed to happen is that the first call invokes both delegates. The second one actually just produces a cache hit for like this value, right? Because it's for the same key, and we know, I mean, the value for this key is supposed to be cached. And now if we, let's say, change the value for this key of a counter, technically, like if we call the second thing right after this line, then it still should produce this thing, right? And basically, nothing, there is nothing to kind of explain to cache that this value is inconsistent. So we could do this. We could basically run the logic for getCounter for the same key inside our invalidation context, which would invalidate each and every dependency of each, including this thing, right? And that's basically what we should do to recompute the output after we change some ground truth. So, so what just happened actually, or like what we just did? In fact, we wrote a caching decorator that supports cascading invalidations. And now, if we look at the properties, then so we still have this call result caching. We also have dependency tracking and cascading invalidation, and we also ensure that the same value is never computed concurrently because of basically this double check locking inside. So, and what's interesting is that we actually didn't change the signature or implementation of any of these functions, right? I mean, the only thing that actually changed here is that now we have to make calls like this when we change some ground truth, right? Some ground truth for deepest dependencies. So Yeah, let's get back to where we started and look on this from a little bit different perspective. In fact, we just built a decorator that incrementally builds every value you request. Incrementally means that it rebuilds just the pieces that changed, right? So if you invalidate something, then it rebuilds just what's changed, and the rest is just gets reused. And in fact, it's nearly what we wanted to get when I started to talk about like why we don't build the UI like this. So there is an animation. It will restart right now. So basically, it's yeah, it's an animated GIF, and we should wait a little bit. And this is how it nearly works. Like if you have a graph of such function calls, right, and if you invalidate result of one of calls, then the whole chain gets invalidated. And if someone some code requests a new value for basically this call, then basically a part of this chain is going to be rebuilt, but these nodes are going to be, or like, sorry, these one are going to be reused. So it's almost the same thing as incremental build in basically MS build or .NET or whatever tool you use. It's just like for any value in code. Okay, and as I said, in some sense, it's or like not in some sense, but it's just a transparent abstraction because you don't have to change the code to use it. And now, like the reason I was showing this syntax with delegates is mostly to illustrate the idea. In reality, the way it works in Fusion and basically you don't have to do even this because we can wrap any service that lives or like that may live inside a dependency injection container with basically something that will provide this behavior for any methods we want. Okay, so now is it how kind of close this stuff to what we could use in production? It's actually very far, and the actual implementation is much more complex because it supports async. It's also GC friendly in sense that, like I said, that these links are bidirectional, and if we just use a straightforward way to kind of keep track of them, then you will quickly end up with basically keeping the whole graph in memory no matter what happens, and so on. So there are like actually many things that I didn't even mention here. But okay, now let's a little bit kind of switch gears and talk about eventual consistency and kind of related technology. So this slide just explains what eventual consistency is. It basically means that like if you stop changing the system, then it will enter a consistent state eventually. And consistent here means that basically the values it shows, or like any output of any kind of query to this system, will produce the same output as like you would get calculating it from the ground truth, right? So funny enough, if you have a cache anywhere, usually usually it always means that your system is eventually consistent. Oh, and for the sake of clarity, being worse than eventually consistent means like you have basically an unusable system because it may stay in inconsistent state indefinitely, right? So now the question is like, let's say we have two eventually consistent systems, and we ask ourselves, are they equal to each other? Or like maybe there are some crucial differences that make one of eventually consistent systems way, way better than another one. And interestingly, yes, there is a crucial difference that makes like, and this is related to what I'm talking about. So, but first let's think of how we usually cache things, right? So if you don't have some sort of explicit invalidation in cache, then what you usually do is you state the expiration time, right? And the trade-off you make is like if you have higher expiration time, then your cache is going to be more efficient, because you like the rate of cache hits versus cache misses is going to be much higher. On the downside, you will see more of inconsistent values. And if you try to reduce this time, I mean, usually if you try to reduce this expiration time in caching to, let's say, 1 second, then it's fine. I guess at maximum you will, so basically 1 second of seeing an inconsistency is maximum you get for any given value, right? But the chance that you get a cache hit is also kind of super low. So ideally you want what was just shown on this slide. I mean, you want a line like this, right? You want values to be stored indefinitely in cache, but on the other hand, you want them to be evicted from cache instantly after, or like quite close to be instantly after they become inconsistent with the ground truth. And so now the question is like, why I like asked if two eventually consistent systems are different. And the answer here is like, of course, like, let's say, if this eventually consistent system almost never presents inconsistent values, or like the chance that you will see inconsistency here is tiny in comparison to this one, then this is much better, right? The reason why it's much better is, well, because you actually don't have to care about these inconsistencies everywhere if the rate of inconsistencies is tiny, especially in the UI. So how all of this is related to real time now? And I guess it's clear that like real time is all about knowing when a result of function changes, or like of some basically thing that produces data changes. And the decorator I shown actually can help with this. It since it basically informs every piece of data that's kind of transformed with the same decorator, that like something changed, so you are probably changed as well. And secondly, it allows to recompute things quickly, because it basically recomputes just what has to be recomputed. So, and I'll leave the last aspect for maybe some other time, or for Q&A, whatever. So let's move on. Okay, and yeah, that's a famous quote on cache invalidation and naming things. So this approach kind of allows to solve a fair amount of pain with cache invalidation. Now, let's talk about React and Blazor a little bit. And I guess, I hope all of you know what Blazor is, but like a short description, it's basically a .NET running in your browser and on top of WebAssembly. So it allows to do anything you can do in regular .NET, or like almost anything, and the exceptions are super rare. And moreover, there is also not only a WebAssembly mode, but Blazor server, which kind of runs all the computations on your servers and delivers the updates using SignalR. So there are a few cons, and the main one is speed. Right now, it's not the same as for native .NET or .NET Core, but honestly, it's not bad. It's not bad, even though it works in interpreted mode. And plus, you can always switch to Blazor server. So and there are lots of pros. Lots of pros. I think the main one for .NET developers is that now you actually don't have to care much about JavaScript. And like you can write anything and share models or some logic with your client-side code. So now let's look at Blazor components. And interestingly, in terms of UI, Blazor copycats React almost completely. maybe improves it in some ways. But overall, that's the markup you see for Blazor components, and it looks like pure HTML markup, right? In maybe a few differences like this, but in reality, it's like JSX. And this is what Blazor produces for such components as basically a code that actually renders them. And you may notice that, like in reality, it builds basically a long list of elements. In fact, it builds what's called a virtual DOM. And once it's built, it compares it with the previous one and identifies changes. And basically, that's how it updates the real DOM. But if you think of like what actually happens here is that like on each iteration, every component basically builds a new version of its DOM, and this new version is compared with the previous one, and like only differences are applied. Doesn't it look like an incremental build of the UI? And in reality, it is. And like you could replace this function with basically a pure function, or like more or less like pure that simply returns this list, and then use basically a logic like this to compare it with the previous one, and just update some components and maybe dispose deleted ones, and so on. So in reality, what Blazor and React implements and what's novel there is this incremental build process for the UI. And like you might ask how it's related to Fusion. Well, it's actually related because it's sort of the same technology already exists for the UI. It's just like maybe you don't instantly see it, but like in fact, Blazor and React, they build UI incrementally. Okay, so a few slides on like why you need to learn functional programming, I guess. Or like these are joking slides, of course, and there are lots of memes in the internet about functional programming, and like even more memes like that. But like in reality, so I don't know if you see the top part of this slide, but functional programming is all about replacing the form with substance. And it allows you to basically declaratively explain what you want to get, and just don't focus on the form. So Blazor and React, they are kind of using the same concept to and benefit from basically using functional programming to build this virtual DOM. And okay, and yeah, and the same for Fusion. So now I guess I sort of answered the question, like, is this decorator really exists? And yes, that's basically not a single decorator, but a whole library that implements many different things. Right now, its state actually is much better. So I made this screenshot maybe like 3 or 4 months ago, and okay, this is the URL you might want to visit. But now I'm going to talk about real Fusion services, and maybe I'll skip a few slides in my presentation and go back to what I was using previously. Okay, let me get back to basically my demo. And now I'm going to show you a couple interesting pieces that you probably didn't notice. So first, the URL here. You see that I was using 2 different ports. And the reason why is that, well, I was running 2 different hosts for this app. Let me show you. So one was on this port and another one was here, right? And funny enough, this state sync powered by Fusion actually worked, and worked pretty nicely. Let me show you one other interesting thing. So I just opened basically another browser window for, so like this was Chrome, right? And right now I'm going to use two Edge browsers, but basically like these are two different windows of the same browser. So I'm going to, nevertheless, I'm going to a different host here. So let me go to user properties page, and right now I'm going to sign out here. Sign out, sign out. What happened? Oh, I know what happened actually. Did I just stop something or what? So it's a kind of blue screen time. This one works, right? And what happened with this one? I don't. 30 works, and oh hell! I guess I should. Yeah, it's not a blue screen. Let me. Yeah. Let me click. Basically, I resumed both things. I mean, when I selected text on basically these pages, apparently logging kind of stuck, and the hosts were not available. So no blue screen, but kind of a glitch, right? My own mistake. Okay, so what I'm going to do now is I'm going to sign out from, so let me actually, yeah, I forgot to change the port. So again, two different hosts, and I'm going to sign out from one of these browsers. You see that like sign out happens in both windows. And if I sign in, it's the same for signing in. Interestingly, if I go to one of these hosts with another user, so I'm refreshing the page right now, and so that's like another user, right? I'm signing out and signing in with the first one, and now I see two sessions of the same user, and I can kick one, kick another, and so basically like it works in every possible way. So I guess the reasonable question is how much of extra code is needed to have this kind of sync. And I'm going to show you the exactly all the code that's kind of needed to get real-time behavior in this app. Oh wait, what just happened? Nice. I think my edge just died by some reason. But anyway, okay, I'm clicking on this link, and basically that's all the extra code that, sorry, that's all the extra code that is needed to get this real-time behavior in this whole app. And it's about 35 lines of code. Oh, this one is not real, by the way, it's from README. So let me show you one of these functions just to clarify how, like what's going on there. So typically the code you write, I mean, if you use CQRS pattern, and Fusion kind of insists on CQRS pattern, and that's what allows actually multiple hosts to sync the state. But anyway, if we cut this block, then it would be an absolutely regular code of command handler for this post message. And I'm returning it right now, but basically it shows that like Fusion makes such blocks for commands running twice or several times. I mean, assuming there are multiple hosts. And what happens there is like exactly these calls that invalidate something. So in this scenario, it's pseudo get tail async for chat, because you may have multiple chat tails, right? And multiple dependently on how long they are. But like if you call this method from this one, then you get a dependency, and to invalidate all the chat tails, you can call simply this one. Okay, and I guess that's mostly, let me get back to slides again. A few examples in these slides. I think I'll leave a link to presentation in, in chat later. But overall, it's about the same. And now the question, I guess, is uh, so how it works for the browser, and like how it works, assuming that like the client, it's a Blazor web app, it runs remotely, right? And well, basically all of this is possible because the box that's used here is actually very easy to replicate. And by the way, like these slides explain basically what happens with like these boxes. Like uh, first you get a box in computing state, and like when it gets computed, then it becomes consistent, and like as soon as it gets invalidated, it gets invalidated and stays invalidated indefinitely while you reference it. And another version of basically the same value might become consistent, and so on. So yeah, I just shown you a demo. There is another one. I mean, there are a few sample apps available, but I'll skip this part. And interestingly, like this computed abstraction, it's fairly easy to kind of replicate it on a remote host, because the only thing that it needs once it gets created is the invalidation message. And basically this shows how you can create a replica locally, right? All you need is to basically subscribe to source invalidated message. I mean, in this case, it's an event, right? And call the same thing on this one, right? And that's how you get a replica of it. But if you replicate the same behavior remotely, then you get like a distributed, well, how to call it, a distributed computed abstraction, or a distributed reactive computing framework. And interestingly, it sounds like it might be expensive, right? But in reality, this is what we typically do. For a regular web app, we usually send a request and get a response, right? And for Fusion API calls, we usually send a request. And since right now the transport is only HTTP, I mean, the only supported transport is like regular HTTP for web APIs, right? Then there is a header that basically indicates that client is Fusion aware. So server should publish wherever is returned. Publish means create a publication. And then regular response coming, but also a header that indicates that there is a publication created on server and you can watch over it. And Fusion-aware clients, they always maintain a separate WebSocket channel to a server, and they basically watch for messages like this one that indicate that certain publication was invalidated. And so in reality, what you get is like, instead of one request, one response, you get one request and maybe one or two responses, and that's it. And that's the cost of real time in terms of maybe extra load on server. But I'll talk about this a little bit more, because of course, like, it also costs an extra memory. On the other hand, you would anyway probably want to spend this extra memory to have a lot of stuff cached, because like with Fusion, you technically don't need much of external caching. Okay, so yeah, there are, and by the way, I think this also worth kind of explaining. So this is how, for Blazor specifically, Fusion provides a package that allows you to implement Blazor components that update in real time. And all you need for such components is to basically write function like this. I think it's, yeah, right now it's named a little bit differently, but something like this. And so basically, these functions, they compute a model for this component. And all of such functions, they are also kind of decorated by this behavior. So they recompute only when it's necessary. And interestingly, since whatever they call is kind of the same nature, right? So it's totally fine to call a method that actually hits the server inside the body of such method, because if this value is the same and client knows that it's the same, I mean, Fusion client, it just wouldn't do the call. I mean, there will be no RPC, it will be resolved through local cache on the client. And once something changed, like let's say the chat tail changed, then like this thing will recompute, but basically the only request that will be really sent to server is this one. The rest will be resolved automatically locally. So that's how like all of this stuff with UI works. And this is another example of UI component. I'll skip it. So, and speaking of efficiency of caching, actually, there is even a sample that shows that it's highly efficient, and plus tests in Fusion test suite. I'll briefly explain, but basically test implements a random reader that just fetches random entities out of, I think, 1 out of 10,000 or so. And they do this in 2 ways. Like one test basically runs straight through EF core, and another one basically does the same with Fusion caching decorator. And just solely because there is this caching, like you may see this kind of speed up. It's not 16, it's actually 16,000, and here it's like 1,000 even for entity framework core in memory provider. So yeah, and funny enough, you don't. So I just said that like if you, let me actually show this very quickly. So there is a website called Board Games, right? And you can just go there. I mean, at any time right now, you can play some games there. It always runs. But the interesting piece is that there is an API. And if you check out like what's your user ID, or actually it's better to use basically these methods, right? Game, or I don't know, chat is a good example. So you can actually post messages using this API, and the API is just regular web API here. So and like the way it works, as I said, is that if you use a Fusion aware client, then all these, sorry, so where are my slides? So all these subscriptions and basically invalidation messaging, it's going to happen automatically. And if you don't use Fusion aware client, you're just going to basically hit the API and get responses, but like you will still get speed up on the server side for server-side caching. And so if you basically don't use Fusion aware client, then that's what one of tests shows, that you get basically 6.5 speed up or so. Okay. So how this like speed up looks like, and right now I'm going to show a couple videos, I guess, and hopefully it's going to look well. So that's the first one. So basically, I guess many of you know what it is, like this is how regular people play games. So like on started and Brie Larson and actually played Captain Marvel, video played paper a little bit more famous. So this is what regular people do, and yeah, I have to hit refresh and go to the next slide. And this is actually what 10x to this looks like. my point is, this is what you could have on your servers instead of like what was on previous video. So what else? Well, yeah, there are a few slides that explain what else you get with Fusion, and I'll, I guess, skip through some of them. It's sort of straightforward. So you get real time and this fancy and very efficient caching without almost zero changes. So interestingly, yeah, I'll just, I guess, skip this. And I guess the main question is like, what's the cost of all of that? And yeah, the library is free. It's distributed under MIT license. Interestingly, it will also free up your CPUs in exchange for memory. And that's where I guess the majority of cost is if we are talking about the production loads. On the other hand, like quite likely you anyway have this memory somewhere, like let's say on, I don't know, Redis or Memcache tier. So with Fusion, you don't need either as much there, or like it will simply live on your basically web machines or like wherever front-end machines or any microservices. Okay, and one other piece is learning curve. It's pretty steep because like, well, I mean, I wish I had more time to document all of this stuff, but I mean, there is a fair amount of material, but it's still steep. And that's mostly it. And if we are talking about real time, I honestly think it's actually the lesser of many evils you would have otherwise. I mean, if it's not Fusion, then probably for any big app, it would be like something that's way more complicated. Okay, and finally, why real time is important? Well, I guess, I mean, I probably like this slide was created a long time ago, but the point is like right now, I guess even the way we run this presentation is like online, right? And many apps that became popular over last year are real-time apps. So I think it makes sense to care about this. And I think this is also why it's important, right, to make changes of whatever, something that's, or like to basically revolutionize, change something that is so old. I think this refresh button in browser is kind of older than many of us. So why it exists? Well, I mean, at the time these browsers were created, there was no concept like even, I guess, Ajax, JavaScript, and stuff like this. So right now we are in much better shape. And by the way, I was thinking of like saying something like, so if I hit F5, then consider it's a blue screen. But I mean, I hit F5 a few times, but it wasn't due to it's Fusion or like samples or wherever. It was my own mistake. So anyway, thanks for watching, and I guess that's mostly it. If you have some questions, I'll be happy to answer.
Awesome. Yeah, I mean, we have one here from Hatan who's wondering, how do you handle the, and I guess going back to some of the stuff you were talking about around caching and TTLs and optimizing for different things, you know, how do you handle cache TTLs in Fusion? And is that like an internal thing for Fusion, or is that something that it provides APIs for, or none of the above?
So Fusion doesn't actually cache stuff in external servers. It caches everything right in process. There is an API allowing to offload something. I mean, so basically, there is an API called swapping, and it allows to offload values that are cached for a while in memory, so that you basically don't consume a lot of memory on your host processes. But I mean, so far, I think and we don't have apps at this point that are so big that I had to use this API. But yeah, that's and if you use it, you can set TTL to any you like, because when the value gets invalidated, the cache will change as well. Sorry, the caching key will change as well. So like ultimately they'll be evicted eventually. Okay.
Cool. And actually, I guess I can see one or two here as well, just out of my own curiosity. So, and seeing that this is a project that's sponsored and housed on GitHub under Service Titan, I'm curious, to the extent that you can actually talk about it, like, how are you all using, Fusion in applications, and if you could speak to any like size and scale or use cases or anything like that.
So right now, scale is fairly small. We use it for some internal services. Like we have a service. I mean, I guess the oldest service that runs on Fusion is basically our dev portal. It's an internal thing that is mostly used to monitor how our microservices are deployed, and basically it just simplifies all this stuff. And yeah, everything is real time there. So it works, I think, from like July or June. And I think so far there were just a few bugs that were really important. The rest was fairly simple. So I mean, honestly, there were no like really important bugs. Yeah. As for anything else, it's more or less. I think so. Service Titan is a big company, and like the amount of code we have, and especially if we talk about the like dependencies of pieces on one or another, it's fairly kind of complex thing. And I think that's why the process of basically implementing something like Fusion is fairly slow internally. So like, I guess I kind of improve the thing faster than we really can implement it. But it's I think it's normal. I mean, it's normal in terms of what we should expect. Yeah.
Awesome. And I guess one other thing I was wondering too, kind of going back to your emphasis of, functional programming and those sorts of patterns, and, that playing really well with this sort of model. How well does or doesn't Fusion play with F# out of curiosity?
I didn't do anything special for F#, but I think it should play pretty well, because I don't think it uses anything that kind of doesn't run on F#. So you can, so if you create your services as basically C# style classes and you use virtual, so like all you need, like in reality, are virtual methods in such services, so that like Fusion can implement their basically proxies in dependency injection container that provide all this behavior with capturing dependencies and like caching and stuff like this. And I think F# supports all of that. I mean, there should be no problems. I don't have an example on F# though. Yeah.
Cool. And we just had one more come in from Hatan as well. So he's wondering how does Fusion handle a web farm scenario?
That's an interesting question actually, because like yeah, I shown in all these demos. I think the reason I shown all of this is that it's actually new. I mean, this behavior, like you can run it on multiple hosts and they still sync. It's like 1 month old. And this was one of the main concerns about like, how do I scale Fusion services then if I don't have this? Because earlier it didn't work. So the way it works is basically every action happening in such an app is described as a command in secure sense. And there is a persistent log of these commands. And also there is a part that's not quite inside Fusion, but basically it's also a part of, I mean, the packages are a part of the same repository. It's called Commander, like similar to Mediator, but basically, I mean, the name is like command R. And so it allows to do a little bit more flexible stuff than mediator, but in particular, it has handlers allowing on one hand to log commands into like the database once they kind of try to access some data context. And basically they do this in the same transaction and so on, and verify that the action is logged. And on the other hand, like if they see that it was a fusion action, then they run invalidation locally, and handlers on other hosts will basically pick up the tail of the log and run invalidations locally there for basically their own parts. So in reality, they maintain the state in sync because they have this persistent log of everything that happened. As for like how they know that like something happened just now, I mean, how they kind of discover. So technically they can do this by pulling like this tail of the log maybe 10 times a second, but in reality, this sample runs on PostgreSQL, and it has notify slash, how it's called, notify listen mechanism, allowing you to basically implement message queues right on Postgre. So it uses, so like basically what's built there, I mean, it's again, it's also a part of Fusion, but it uses this mechanism to notify other hosts that like persistent log was updated. And so they have to read the tail. So that's why it's instant.
Cool. One more came in as well. So, wondering. So I think you mentioned that the protocol for Fusion is HTTP or HTTPS. Wondering if you have any plans for gRPC support.
Yeah, there are plans. But I don't. I'm not fully sure when I'll get to gRPC. The second problem with gRPC is that it's strongly typed in the sense that I think, sorry, not this one, but right now you can't, I think, serial, or like there is basically nothing that allows to serialize generics, and I mean, use open generics as the part of basically messages. And Fusion right now uses this part. So even if it's going to be gRPC, I think in reality it's going to be something like message pack on top of gRPC. So I think that's one of the things, but the important part is actually like the throughput of server, even running on HTTP with Fusion, is something like 100,000 messages per second on like my machine. So technically, performance and like bandwidth of a channel is not the limiting factor. Let me show you, if you see my screen, let me show you actually one thing. So there is, so this thing runs like remotely. It's not on my machine. I just go to basically this, sorry, how to zoom it so that like, okay, I don't know how to zoom it, but my point is like, you see that this is a sort of screencast, right? Right now, I think is it, what kind of Blazor it is? I mean, okay, it was Blazor server. So right now, oh, nice. Why it doesn't? Yeah, so something is off. I think this, yeah, I've made some updates today, and basically I had to update this sample to older version. I don't know why, but like it means that something kind of, yeah, doesn't work on WebAssembly. Okay, I don't want to, yeah. Something is definitely off here. So anyway, I guess I'll fix this today. My point is, even with HTTP and a tech like this, basically this is nearly the like rate of messages you may expect to get, and it's probably like 20 plus per second. And so bandwidth and like I don't know, like latency related to HTTP honestly is not the biggest factor right now. Okay.
Cool. I think that actually lends itself nicely into what I think will be our last question. But anyone who still has anything top of mind, feel free to chime in before we close up. But what does the observability story in Fusion look
Yeah.
like? Like, how would you actually know what your throughput is and how well you're tuning things and all that?
Yeah, you need to. I don't think there is a lot on Fusion side that may help you to kind of monitor all of these. But on the other hand, as I said, like it's actually a regular. So if you are talking about servers, then you have a regular web API that you can monitor by using every usual method. I think what makes it a little bit special with Fusion is that you probably want to know when something gets invalidated, and yeah, there are ways to plug this into basically this part of the pipeline, but overall it's totally possible. So the short answer is like you probably have like 80% of tooling you need, because it's mostly like usual stuff. As for the missing extra, it's not a huge piece of work. Basically, that's the answer. Yeah.
Cool. I think that covers everything that we had. I guess if anyone has anything kind of last minute, feel free to chime in while I'm giving the kind of closing spiel here. But mostly I just want to say, Alex, like this was really awesome. That looks like a really cool library that you built too. That takes care of a lot of the really hard work. So those are always the best kind of libraries that in my mind. But really appreciate you running through all this, taking the time. Really awesome content, and appreciate everyone for asking questions as well. Like I said up front, that's really what keeps this a lot more fun than just kind of giving one-way communication and conversations and stuff. But once again, I really appreciate everyone coming out for this evening. This recording will be up on our YouTube channel sometime in the next couple days. My computer freaked out for a couple minutes, so there might be a weird blip in there. I'll see after I stop recording how that turned out, but everything but 2 minutes at the very least is good. But Alex, thanks again so much for coming out. It was awesome to have you.
Thank you, guys. Thank you.
Cool. And we'll have news up of our next meeting real soon, so keep an eye out for that. But in the meantime, I hope everyone stays safe and healthy, and we'll see you soon. Have a great night, folks.